We'll start. Hearty welcome to the 56th distinguished lecture being organized jointly by INAE Bhubaneswar chapter, IIT Bhubaneswar, IMMT Bhubaneswar, Niger Bhubaneswar, SOA University, and the IEEE Bhubaneswar section, and your host is SOA University here. So today, I'm very happy to say that Professor Nitin V. George has kindly agreed to give this lecture at very short notice. And for your information, Professor Nitin George has got connection with IIT Bhubaneswar in the sense he is the first recipient of PhD from IIT Bhubaneswar. Now, regarding his background, Professor George received his BTech in Electronics and Communication Engineering from University of Kerala and MTech in Telematics and Signal Processing from NIT Rourkela. He was awarded a PhD in Electrical Sciences from IIT Bhubaneswar in 2012. He was the first graduate of the institute. He joined IIT Gandhinagar as a faculty member in Electrical Engineering in 2012. He is currently at TEO-CO chair, professor in Electrical Engineering at IIT Gandhinagar. His research interests include audio signal processing and array signal processing. He has published over 75 articles in top international journals. He received the Department of Foreign Affairs and International Trade, Government of Canada, GSCP Fellowship in 2008, Inspire Faculty Award in 2013, Indo-Australia Early and Mid-Career Research Fellowship in 2017, Excellence in Institution Building Award of IIT Gandhinagar in 2018, and Excellence in Research Award of IIT Gandhinagar in 2023. He served as the Associate Dean of Postgraduate Studies at IIT Gandhinagar from 2015 to 2018 and Associate Dean for Faculty Relations from 2018 to 2022. From 2022, he is serving as the Dean of Academic Affairs at IIT Gandhinagar. So far as Professor George is concerned, he has got very strong connection with not only IIT Bhubaneswar, but also NIT Rourkela, and of which I am also a graduate. And here also you will find Professor P.K. Nanda, who is our Honorable Vice Chancellor. He has also served in NIT Rourkela. Professor George, you might have seen him there. Hello.
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 Yeah, yes, sir. I met him here also at IIT Bhubaneswar, IIT Gandhinagar.
Gandhinagar we met.
Okay, fine. So, of course, I'm not going to read his abstract. Anyway, it is given, and he will explain all these things. Now, our Honorable Vice Chancellor is present here. I will request him to say a few words as actually co-sponsors of this lecture series. Professor Nanda, please.
Thank you, sir. Good afternoon, everybody, and Honorable Chairman of this INAE Bhubaneswar chapter, and also our Chairman of our Advisory Board of Sikha Anusandhan University, Professor Damodaracharya sir, all the distinguished fellows and members and participants, faculty colleagues, and students, and especially Professor Nitin George, actually you might know him also. I met him at Gandhinagar, and yes, he's a very good researcher. And we welcome to this lecture for this INE lecture series. And also we'll welcome to our university sometime. So you are there at IIT Bhubaneswar. So as regards the university, I think many of us know, I think for your I think information, Professor Judge, that this university is actually ranked last year 14th rank in NIRF, and the engineering institute is now 26th and medical is 21st. Two of the institutes, kind of the dental science and legal studies, are top 10, 9th. And also in QS ACR ranking, we are 278 positions. And THE also we are 300 to 350. World ranking also we are there in 1000 to 800 to 1000 in THE, put 1200 to 1400 in QS. So we have currently 20 research centers, 60 research labs, and many extension activities. Recently, lastly, we established the Center for Quantum Science and Technology, and that's also picking up well. And as regards the other activities, our university also has got other awards regarding the Swachhata Award, the other kind of the small awards. And the university is also appointing many adjunct professors from abroad as well as India for the joint research activity. We have 2 joint research of BRICS research project as well as Thailand, Malaysia, that is DST and ASEAN countries project. Besides, we have 115 research projects across different disciplines. So currently we have 14,500 publications, Scopus Index, out of which 9,000 are Web of Science. So our that's what H index is more than 120. And that's what the research contribution. We have 1,100, 1,300 now 63 research scholars. 500 of them we are funding and sponsoring. Remaining some of them get from 40 from the different sponsoring agencies, government agencies, and rest are some self-sponsored and part-time students. So this is in brief about our university, and we are happy to be part of this series lectures which you have been conducting. I also thank Professor Damodar to look in very good research across the country for this lecture series. Thank you, sir. Thank you very much.
Thank you so much, Professor Nanda. May I request Mr. Tripathi of actually IEEE Bhubaneswar section, also our co-sponsor for this series of lecture, to say a few words.
Thank you, Dr. Acharya, for giving an opportunity. IEEE has been active in Bhubaneswar since last 10 years. We were a subsection earlier under Calcutta Union branch, and now since last November 23rd, we are an independent section. We have got 11 society chapters, 5 affinity chapters, and all the important institutes, engineering colleges in Bhubaneswar are members of our society. We have 2 objectives. One, to work with the INAE together and important institutes in Bhubaneswar to increase the membership of both the organizations and have interactions, technical interactions as much as possible. I am pleased to say that many very learned professors in many organizations here have started taking interest. Recently, we have even had a very interactive industry and IEEE interaction meeting, and we are hopeful that organizations like Odisha Power Transmission Corporation, SLDC, and OPGC, they will be taking part and actively working with IEEE. Our objective is to see that IEEE culture spreads into the societies and the institutes in Bhubaneswar, and more people join various societies, and we have technical interactions with them. And this is encouraging the overall objective of the government as well as the institutes in Odisha for better industry and academic interaction. And I am very pleased that Dr. Acharya is sharing these meetings, and we have on the 56th meeting. and we are also keeping record of the meetings. Soon we will have a forum where we can have many kinds of activities involving both the organizations and take both the institutes ahead. Thank you so much for giving the opportunity.
Thank you so much, Professor Tripathi. Now may I request Professor George to take over from here onwards.
Yeah. Thank you, and thank you everybody so much for attending and for arranging this talk. I think I am audible. Yeah, correct, sir? Yeah. So the talk today is on microphone array signal processing and beamforming for hearables. What I am trying to do is I try to understand all the terms, the hearables, what is array. So the flow which I am trying to do is that I will just have an introduction of what is the area. I will talk a little bit on hearing loss and assistive listening methods. Then I will talk about some challenges in hearables. So hearables is essentially a wearable which is in the ear. That is a generic term now which has come, which is called a hearable. Okay. So this includes the smart headphones, the smart earbuds which we put on in your ear, the hearing aid. All of those can be brought together in this broader term of hearables now. And then we talk about some of the challenges and some of the ways in which these challenges can be solved. And one of this method is called microphone arrays. Microphone arrays means you have an array of microphone elements, and which you see in many of your equipment around you, including your...
Could you please a little louder?
Oh.
I think noise is coming.
Fine. I will be louder. Yeah. Is it better now?
Please.
Yeah. Fine. Yeah. Microphone arrays, and then I will talk about direction of arrival estimation.
No, that audio interference is still there.
Yeah, sir, I think Professor Ajari, I think if you mute it, no, I think it should be okay.
I think we'll all mute. We'll...
Yeah. Hello. Yeah, Professor Ajari, I think if you mute, this feedback will be stopped. Hello.
Hello.
Yeah. I think, is it better now?
It is better now.
Yes. I think we got a right start for the session, because when I am talking about acoustic feedback cancellation, this is exactly what I wanted to tell about the feedback which is there. So I think that is the right beginning for the talk. And then I will talk about how noise reduction and beamforming will come into hearable. So this is the way I have planned the talk. Okay. So before I go there, let's first understand what is the problem which we are looking at and how big or how difficult is the problem. So as per WHO estimate, 2.5 billion people are expected to have hearing loss by 2050. And over 1 billion people are at the risk of permanent damage of hearing. And what is the cause for it? These causes includes prolonged digital audio exposure. So this is something which has come post-COVID, I would say. Prolonged digital audio exposure, rising noise level, unsafe listening methods. All of these can cause significant problem as far as hearing is concerned. And what WHO is saying is that 2.5 billion people will have hearing loss by 2050. And what WHO has put a new term for this, which is called, is this the new diabetes? Means where it is going to be very common among people. But if we are not addressing this problem, what are the type of impact? What is the cost of inaction? This also WHO has given this, saying that this can lead to delayed language development for kids, cognitive decline, academic underachievement, social isolation, and all of those issues can happen, and also lead to significant cost of the order of $980 billion annually is what WHO is estimating.
Sir, can you go to full screen, please? We are only getting,
yeah, in this is the only mode available. Yeah. Okay. Yeah. So what is a hearing loss, and how do you know whether you have a hearing loss or not? So if you are not able to see something clear, you already know that you are having a problem with your eye, because you are able to read something clearly earlier. Now you are not able to see that clearly. So I know I have a visual problem, and I will go and get it tested, and I will put an eye. So that is a very straightforward problem. But that is not the case as far as hearing is concerned. So the problem is, I don't know whether the problem is with me or whether the problem is with somebody who is speaking to me, whether somebody is speaking low or whether I am having a hearing loss. I am confused. So mostly people will not even know that they may have a hearing loss until you reach a extreme or a slightly severe stage of hearing loss. So how I understand whether I have a hearing loss or not is I do what is called an audiogram. So I go to an audiologist, they will create an audiogram for me. That is a frequency versus volume plot, where they play different types of frequencies into your ear, the left ear and the right ear separately, and then ask you whether at the particular volume you are able to hear or not. If you are not able to hear, they will increase the volume and see whether you are able to hear at this volume level or not. Okay. And then they plot this graph, which is called an audiogram. So the meaning is, if I have a frequency of 250 hertz, and if the amplitude is above level 10, I am able to hear. But if I look at a frequency of 2000 hertz, if it is above 10, I am not able to hear. I will only able to hear when it crosses this level. That means 35 level. Understood. So when it comes to 4K, it says that it only if it is above 70, I am able to hear that. So I may have a difference in amplitude levels for different frequencies which I am able to hear. And when I have hearing loss, this curve can also change. That means you may have a hearing loss at a particular frequency, maybe 500 hertz or 1000 hertz, but you may not have a hearing loss at 4000 hertz. It can be the other way also. So this is frequency dependent parameter. It is not like a single number which can be assigned to you, saying that like a glass is prescribed to you, saying that it's you are minus 2.5, minus 3.5, something like that. I can't give such a number to you in the case of your ear, because there is a significant frequency dependency. So for every ear, for your left ear and your right ear, you have such an analysis can be done to understand what is the threshold of hearing for you for both your left ear and the right ear. Now that we have identified that you have a problem, there can be multiple types of hearing losses. One is called the sensory neural hearing loss. One is called the conductive hearing loss. Another is a mixed hearing loss. Most hearing losses because of aging, because of noise damage, can be considered as sensory neural hearing loss. So what we are saying is that you are able to hear at level 10 earlier before your hearing loss. Now for the particular given frequency, and now you are able to hear that particular same sound now only at 20 or 30. This is the idea of in a very crude form. So the simplest solution to such a problem may appear like what is called a hearing aid, which in the simplest form can be a microphone, an amplifier, and a speaker. This is the simplest diagram of a hearing aid. But this amplifier is not supposed to amplify all the sounds equally. It is supposed to look at your hearing profile and provide amplification according to your hearing loss. So that means every hearing aid is custom made. So there is nothing like a generic hearing aid, because your hearing loss on your left ear, on your right ear, for you, for other people around you, everybody has a different profile. That means this system has to be custom made. So this is the simplest form of a hearing aid, where I can say I have a mic, I have some sort of an amplification, and I have some sort of a loudspeaker. But this is not such a very simple trivial problem because of several reasons. For example, if I am putting an amplification, that means the noise in my background is also going to get amplified, because as a hearing loss person with hearing loss, my difficulty is I am not able to communicate properly with the person in front of me. That is my biggest difficulty. But I am my hearing aid is trying to amplify that sound, but there are so many background noises. These noises are also going to get amplified. So that means I need to have some mechanism of noise reduction. So this system should have a noise reduction. That clarity is there. Second is, one major difficulty, especially for people with hearing loss, is when multiple people are speaking simultaneously, and I want to listen to a particular person and not get disturbed by sounds from another person. I need to worry about directionality of my sound. I need to understand, or my system or my hearing aid should be able to understand from which direction my sound is coming, and can I only pick up sound from a given direction and ignore sound from another direction. That is something like a spatial filtering. Spatial filtering means in space I have a filtering operation where I am picking sound from one direction and not picking sound from another direction. So directionality is another concern. First is the noise reduction, second is the directionality, third is the problem which we just now faced. So the problem which we just now faced is that this microphone, so this microphone is picking up my sound. This loudspeaker is giving my amplified sound, but the output of the loudspeaker is fed back to the microphone. So the amplified sound which is coming out of the loudspeaker is given to the microphone, which is further amplified, and a loop is getting created. So that was what was happening earlier, because my sound was picked up by the microphone, amplified by the system, and played on a loudspeaker. It was on a speaker mode. In one of the user or some of the users were on a speaker mode, correct? So the speaker produced that sound was picked up by the microphone of that particular user, and this entire loop was created. So the solution which was done over here is that we switched off that microphone. We somehow tried to break that loop. So this problem is called acoustic feedback. That means this system, the hearing aid which I'm going to wear throughout my day and throughout my night, should have a feedback canceller also. So that is another challenge which is there. So my device should have noise reduction. My device should be able to understand direction of arrival of sounds, pick up only sounds from particular direction, also do feedback cancellation. Why this feedback is coming is that if I look at a simple hearing aid or a hearing device, assistive listening device, I have a mic and I have a speaker. Okay, and this mic and speaker are close to each other, correct? Because they are close to each other, and because this is a hearing aid aimed at providing higher amplification, this feedback is unavoidable. So this feedback will anyway happen. So I should be able to do some sort of a digital cancellation of my feedback. That is the idea. Because typically in meetings, when we have this whistling sound, what we normally do is that we either go and reduce the gain, then that problem gets solved, or we move away from the loudspeaker and move to some other place, the problem gets solved. Those two solutions will not work in this problem, because this person is already not listening. So reducing amplification is not a solution. Second is I cannot separate the microphone and loudspeaker due to some reason which I am going to say in a little bit time. Why this microphone and loudspeaker should not be separated is because I want to use my pinna. I don't want to have a situation where I have mics on my glass or on my in the front, because I want to use my head as an opaque object between two ears and use that to identify from which direction the sound is going to come. Okay, so if I want to explain the problem again, the problem is, the first problem which we are looking at is called acoustic feedback, where the output of the loudspeaker, in addition to going into the eardrum, is getting picked up by the microphone and amplified again, and a loop is getting created. Now, can I create an electronic solution to this problem? That is the first problem which we are looking at right now. So our problem is this, that we have a path over here and this is getting this. Now the solution is, can I create a model or create an equivalent system of this path from point A to point B? From point A to point B, if I can replace this entire path means the loudspeaker, the air path in between the microphone, the point A from point B, if I can replace it by a box which I can design electronically, then if I give an input A to that box, whatever output B I am going to get should be equivalent to if I give A over here and get B over here. Understood. So that means if I am able to somehow create an equivalent electronic system which models this physical path from capital A to capital B, I may be able to cancel that feedback internally. This is what is being done over here, where this adaptive filter which is mentioned over here is essentially trying to model is trying to model that acoustic path which is going to be over there. So what happens is when I move my head, the path has changed. So my model also should be changed. So that detail mechanism is not available here. So when I move my head, my path will change. Feedback will be there. Some whistling sound is trying to come, but algorithmically I'll try to internally generate this signal and then try to cancel that signal over here. This is the basic idea of an acoustic feedback cancellation. So essentially what I am trying to say is there is a path, feedback is there, feedback cannot be removed by usual methods. I generate an internal signal and try to cancel it. Another possible question which is over there is, can I put some sort of a filter over here, and remove the feedback? That is also difficult because the speech which is coming and the feedback which is coming are similar. That means they are of same spectral region. So you cannot put a low pass or high pass or some sort of a filter to separate or cut them, correct? So that is also not a solution to the problem. So we may have to go for an algorithmic solution to this problem. So that is about feedback. Okay, now this is what I was trying to say. So essentially we will have to create models of physical systems and which is going to be used in our algorithmic design. So for example, if I want to model this path from A to B, what I essentially do is I'll try to do a, what I can say, something like a supervised learning type of an approach, where I give an input to the actual physical system, get an output of the physical system, give that input to a model. Model is an electronic model with multipliers and adders and delays, and then get an output over here, find the difference between the response of the physical system and the actual system, and then use some algorithm to learn that model. Okay, so the model will get learned and finally I will be able to create an equivalent circuit which will be able to reduce the feedback. Okay, so I am skipping 2-3 slides because there is some math there. If needed, we will come back. This is one typical implementation of a feedback cancellation, where what we are trying to do is that there are so many different types of electronic blocks which are available over here, which will run in parallel, and some algorithm is going to run in your hearing aid, which is going to finally do the cancellation. So the problem which we were looking at earlier about acoustic feedback is always there in hearing aids, but it is algorithmically cancelled inside a hearing aid. Okay, so that is what is over here. Because our topic is on array, I will focus more on that topic. And typically what we do is that when we design these type of algorithms, we will have to check whether my algorithm is working or not. So we create prototypes and test on these type of devices. This device is what is called a dummy head microphone. So this is a head on which I can put the newly made device, and inside the head there are microphones which will measure whatever you are listening inside your ear. So I will be able to measure and see whether my algorithm is working properly or not. Okay, so this was the first problem we were looking at. Second problem we are looking at is directionality. Directionality is I want to understand from which direction sound is coming. Because as I said in the beginning, I have two speakers speaking to me. I want to listen to one speaker and I don't want to be disturbed by the sound of the other speaker. It's like a party problem. Second is I'm trying to speak to somebody, but there is a loud noise which is there in my background. Some mixer is on or something is on. Okay. But if the amplifier, if the hearing aid is going to amplify both, then it is of no use. So I will not be able to listen to the speech which is desirable for me. Okay. In such conditions, what we do is we use microphone arrays. So microphone array is just a set of microphones arranged in a particular geometric shape. It can be linear, it can be rectangular, it can be spherical, it can be arbitrary configurations where microphones, multiple microphones are connected together in a particular fashion. This is one product which is available in the market. This is a Sennheiser Team Connect. This is like a tile which is put on your ceiling, but this is a 28 microphone array where there are 28 microphones which are there in this one tile. If this, suppose this type of a tile is used in a room, in a conference room, then I may not need any microphone for any user who is sitting in that conference room at all. All the signals from each of the speaker is going to be picked up by the ceiling mic array which is going to be over there by directing by selectively picking up sound from the active speakers, something like that. That is the main idea. This is one product which is available in the market. So if I want to selectively pick up sound from a particular direction, I should first be able to understand from which direction my sound is coming. Okay. So that is what is called direction of arrival estimation. So direction of arrival estimation means I have an array of microphone. I have set up this array of microphone and I want to understand from which direction the sound is going to come. So the basic principle is that suppose sound is coming from this particular direction, and if I have an array of microphone, this is one mic, this is another mic, this is some nth mic. So there will be a finite delay between the sound reaching the first microphone and the second microphone and the mth microphone. There will be a finite delay between these. I could use that information. This will also lead to a phase shift in the output. So I can use that information to mathematically estimate from which direction the sound is going to come. Okay, so this is the basic crude idea about what is a direction of arrival estimation, where I have little bit of math in the sense this is the original speech which is going to be there, and these are the phase delays which are going to be added, and then there will be some noise. So you have an array output in the sense instead of one mic and one output, now I have a set of microphones and a set of outputs. Okay, so I could use this information to actually estimate the theta from which direction the sound is going to come. I'm not explaining that right now, but I can use that to do feedback cancellation. In the sense earlier I said we were doing feedback cancellation by electronically doing the cancellation. I would also do what is called a beamforming. Beamforming, you would have heard in antennas, there is a lot of beamforming which is used. Beamforming in the sense, instead of picking up sound from all the directions which are there, I can create a particular beam and pick up sound from one direction and create nulls in the other direction. This is the basic idea. So because my desired speech is coming from this direction and the feedback is coming from this direction, I could now create a beam such that the beam is directly focused on the outside speech and not on the speech which is coming from inside. That creation of beam is called beamforming. So this is a standard term in antenna which has been borrowed now into microphones and speakers, where we can actually say I can selectively pick up sound from a particular direction and not pick up sound from other directions. This is very useful in hearing aid in addition to feedback cancellation. In a normal conversation, when I am speaking to somebody and then there is this background noise, I can focus my beam on this particular direction of the desired speaker and only listen to that speaker and ignore whatever is there in the background noise. Okay, I will try to explain this beamforming is what I am trying to explain, try little bit better here. Okay, so this is the type of setup we use for testing hearing devices, where this is the head, dummy head, which I discussed earlier, and these are some this is a processor, it's called a speed goat real-time target machine, where we run this algorithm and also do this experiment to see whether all of these things are going to work in real time. Okay, so let me explain one uh, beamforming case where our objective is to capture speech from a desired speaker when multiple speakers are talking at the same time in the presence of background noise in a reverberant room using a microphone array. This is the problem statement. So I have to capture speech from one speaker, that is the desired speaker. This is the direction of the desired speaker. Then there are several other speakers which are there in the room. They are trying to talk. And this room is also a reverberant room. Reverberant room in the sense, if I generate a sound in the room, this sound is going to be reflected by the wall, reflected by the ceiling, reflected by the furniture, and so many multiple versions of the sound are going to be there in the room. So when this microphone is going to pick that sound, microphone is not only picking up the sound of this particular person of desired speaker, but also other speakers, but also the reflections and reverberation which is already there in the system. And from all of these, we have to identify and target one particular speaker in that room. This is our objective. And what we are trying to do is we are trying to use a circular array of microphones. So this is my circular array of microphones. So I have put n number of microphones in a circular fashion, and I am trying to do this particular task. So our objective is there are P microphones which are there. There are D speakers which are there in the room, and whatever signal is captured by our microphone array can be given by this equation 13. Okay, so the meaning of this equation 13 is there is this one term A which says it is the acoustic transfer function from the dth speaker to the microphone. That means when I have n number of speakers in the room, there is a path from that speaker to each microphone. There is one, you can draw a line, for example. Okay, so this line from here to here, for example, path A to B, that has got some sort of a transfer function or some sort of an impulse response or some sort of a system behavior. So A to B path is a system for me. So the signal which is getting transmitted from the source, from each of the source, is getting modified by this transfer function before it reaches the microphone. So the speaker D or speaker A or speaker 1 is speaking at a particular location, but the sound which is picked up by the microphone is not exactly the sound at speaker 1 location, but speaker 1 location which has passed through a path from speaker 1 to the microphone, and that is what has been picked up. In addition to that, there are interfering noises which are going to be there. So this is the composite signal which is picked up by the microphone array. So this X is a vector now because there are P number of microphones which are there. So P different outputs are going to be there. Okay. So if I look at the array, 1, 2, 3, Pth microphone, each microphone will have a signal which is a combination of speech from speaker 1 plus speaker 2 plus speaker D plus background noise. All of those are going to be mixed together. And now my desired direction is this omega D. Omega D is the elevation and azimuth direction of the Dth speaker, which is of my interest. I am interested in picking up sound from the Dth speaker and ignore all other speakers. So that is my objective. So somehow, given equation 13, I should be able to estimate by omega D. if equation 13 is only given to me, can I estimate my omega d is the problem statement in this beamforming problem. Okay. So what we do is that, so our objective is to capture speech from a particular direction while rejecting speech from other direction. So this is our objective. So what we do, on top of the signal which has been picked up by the microphone array, X is the signal which has been picked up by the microphone array, I multiply that output by another matrix actually, which is a filter. So what I am going to do is that this mics are giving some output. This output are going to be multiplied by some sort of a values, and then I am going to add all of them together to get something. Okay, so I am going to do some sort of a weightage on top of it, and then I say I am going to I am going to yeah I am going to find out what should be this W, what should be this W, so that sound is picked up only from the omega d direction. Okay, so one small mistake I think I said is estimation of omega d is a direction of arrival problem. Okay, estimation of arrival omega d is a direction of arrival problem, and once the direction is already known to me, now my problem is find out what value of W should be selected in this filter such that only sounds from that omega d is picked up. So we use something called the beamformer. One example is something called a minimum power distortionless response beamformer. The meaning is I am trying to minimize the power, but if I minimize the power, then no signal will come, with a constraint that this filter, when applied to the input from that particular direction, should not create any distortion in that particular direction. That is the vague idea of it. Okay, so the vague idea is I am trying to minimize the power, but with a constraint that there should be no distortion for the signal which is coming from a particular theta d direction. That is our objective. So that is not going to solve our problem. So we are going to make a big assumption on this, saying that whatever Zs which we are going to get, what is Z? Z is the output of the filter. Output of the filter is Z, and this Z should follow some sort of a probability distribution. So we are saying this Zs which we have estimated, which we are getting out of the filter, is supposed to follow a particular probability distribution, which we know is the behavior of speech. If I take speech and if I look at the probability distribution of speech, speech is supposed to follow some probability distribution, and this output of the filter should also follow some particular type of a probability distribution. That is the vague idea of this problem statement, where in the first case, we are assuming that a complex Gaussian prior is what is assumed, where we are saying the probability of this Z, probability distribution, should follow a complex Gaussian. This is our simple complex Gaussian only. But there are so much of, what I can say, different time indices which are going to be there. So in every time and frequency, if I have a time and a frequency, for a given frequency, there are different time for which the speech is going to be available. So for all of those together, it should follow this type of distribution. That is the main idea. Okay. So then what I do, I think I'll just quickly go through it. What we try to do is essentially try to find out what could be a good value of W, which will make sure that the output of this filter follows a distribution which is assumed by us. Distribution which is assumed by us. Okay. So if I do that sort of a derivation, what I will get is I will finally get a W, in the sense what should be the weight which has to be put for picking up sounds from a theta d direction. This I will be able to calculate mathematically and I will be able to do that. But it is not necessary that my assumption of a prior is proper. Because if I don't assume my prior properly, because I made an assumption that it is Gaussian. Okay, but there are speech studies which says that a Laplacian prior is a better prior as far as speech is concerned. So I could also use a Laplacian prior to say that this is supposed to follow a Laplacian prior and not follow a complex Gaussian prior. And I could develop algorithms, maximum likelihood estimation algorithms for doing this type of a beamforming. Okay. So if I want to look at some result, I will show you some result. This is for a room of 10 4 meter cube, where I have two speakers which are there. First speaker is at 60-135 and second speaker is at 60-45. And I have a microphone array of 7 microphones. So my objective is to find out, can I only select speaker 2 and not select speaker 1? That is our objective. So these are some of the results. So this is the spectrogram of only speaker 1. This is the spectrogram of only speaker 2. And normally what happens is when I have a mic, these two speakers will get mixed together. So now what you can see is that the speakers are going to get mixed together. And now my algorithm should be able to separate these two speakers after the beamforming process is over. Now you can see here, this is one of the algorithms where you can see this time frequency plot is similar to this time frequency plot. And this one is similar to this one, where even when both the speakers are available together, we are able to separate those two speakers and take out only one speaker from a particular direction and not pick up, not getting interfered by speech from some other direction. Okay, so this is the major idea which is being used over here. Okay, so this can be also done using different type of arrays. It can be done on a spherical array as well. In a spherical array, that may not be very much useful in a hearable, but this is lot of work is there on different types of arrays and how that can be utilized, which is going to help us. So this is like a typical spherical array where you have microphones, and microphones are on a sphere. So here you will be able to now estimate in which direction in the entire azimuth and elevation you will be able to find out without any confusion from which direction your particular source of sound has come. Okay, so this is some result for, again, for a spherical array which has been done, but you are not able to make out lot of things from this. So what we also have is we have some objective measure to evaluate whether the estimated speech which is coming out of the beamformer are what you can say good or not. Okay, some of the measures which you will see, one is called the capstral distance. Okay, that is one sort of a measure. Second commonly used measure is what is called a perceptual evaluation of speech quality. So if I have a speech which is distorted and if I have a clean speech, I will be able to identify how much distortion is there, and after I do a denoising, how much improvement has been done, I can get using this measure called PSQ. These are some numbers. So this algorithm is going to give me some number saying that which one is better and which one is bad. Okay. So for example, if I look at PSQ, when I was using a normal what you can say beamforming algorithm, I was getting a 1.114 as a PSQ. It's a score. And after I use the method which I discussed earlier, we get a 2.01. This number is up to 4.5 in terms of speech. But this is for a reverberant room, means lot of reflections are there in the room. And you get an improvement in terms of this, and this will improve the speech qualities which is offered to the person. Okay, so there are some other measures which are there where we can also see that there can be improvements which are going to be there. Okay, This also has application in speech recognition, means automatic speech recognition systems, where we can also look at word error rate. Means if I play a particular speech, you do a particular model for converting speech to text and then see how much word error is going to be there. And if your word error rate can be low, then your system is going to be better. Okay. For example, here you can see the word error rate was very high, and after you apply these algorithms, this can be very low. Significantly, it can be reduced in this type of a system. Okay. This is an experimental setup which we did over here on something called a sector microphone. So you don't need a full sphere. You have a sector of mics, and it's a different math which is going to come to again do a similar type of a problem of selectively picking up sound from a particular direction. Okay. So you can see that this has been now become very popular in so many devices around us. For example, the Apple HomePod, the Amazon Echo, all of those have having several microphones inside. That's why even if you're calling it in the presence of noise, you're calling Alexa, Alexa is able to listen to you and also try to understand what you're trying to speak, because all of those have been made possible by using these arrays of microphones and arrays of speakers. Okay. And this has become significantly used in wireless communication now in terms of massive MIMO, and this I will not this is not just as an example I mentioned, because these terms will come across several different types of areas. Okay, fine. The last thing, the second last thing which we want to look at is noise reduction problem. Noise reduction problem in the sense I said, when you are going to amplify, your noise is also going to get amplified. Now the noise reduction problem is to see how the speech is getting amplified, but the noise is not getting amplified. So that is the problem. This is a machine learning solution to the problem, where what we are trying to do is, I will just give you an idea about how this has been implemented. So what we are doing is, we have an input speech which is there. I create a buffer, in the sense a vector of that speech. I go to the time frequency domain for the particular speech. As far as once I go to a time frequency domain, it has a magnitude and a phase information. So if you look at the magnitude of a speech, the magnitude of the speech will look something like this. This is the magnitude of the speech plot. So this is just like an image for me, because this is the representation of magnitude of my speech. So if I have speech which has been corrupted with noise, that means that image which is going to be there is corrupted with noise. So I could use an existing denoising model, like something like a, what you can say, image denoising model. I could use and create a new magnitude plot which is not containing noise but contains only the speech part. But if I want to listen to that sound, I need the phase information, because there is a time dependency on that speech. So I retain my phase information from the input and mix it over here with the denoise version of the magnitude spectrum. Okay, so I have a magnitude which has been denoised. I have a phase which is going to be there. I am going to mix them together. And once I go back to the time domain, I will have a denoise version of the sound. So this is some sort of a noise reduction which can be implemented in this type of a system. Okay, where our assumption is the noise is additive, noise is on the amplitude, noise is not in the phase information. Then the last one which we will look at is what is known as an active headrest system, which we have done some experimental work. So that's why I'll just show this. So the active headrest system is essentially a headphone which does noise cancellation, but there is no headphone. So the noise cancellation is done on the headrest or the chair in which you are going to sit, and not on a headphone. So you don't need to wear a headphone, or you don't need to do a noise cancellation. Why noise cancellation is becoming critical in hearing assistive listening is, for example, you are going in a train and you are listening to music. So because you are in a train and you are listening to music, what you will do is you will have you raise your amplitude, volume, and you listen to music at a higher volume. So you are aiding to hearing loss in the upcoming time, because you are deliberately increase your volume, because you are not able to hear because this train is making so much sound. This is the scenario. But now suppose I am using a noise cancelling headphone. What this noise cancelling headphone is able to do is actively reduce the noise level. So now I don't need to play my sound at a higher volume which we were playing with a normal headphone. So I am able to now listen to sound at a much lesser volume compared to what I was listening earlier. So this is the power of active noise cancellation. So I am paying 5,000 or 10,000 or 15,000 for an active noise cancelling headphone, but that is indirectly actually helping me retain my listening for a longer period. So this is the idea. So what we are trying to do over here is that, because wearing a headphone may not be comfortable always, so can we have the system of noise cancellation incorporated in the chair itself, not on the headphone? This is the idea of active headrest system, where what we are trying to do is that we are saying I am trying to cancel the sound or the noise around the ear of the person without the person wearing a headphone. That is the idea. Where the idea is that the chair will have speakers which will try to produce some sounds which are going to cancel sounds which are coming from the noise sources. For example, there are these noise sources which are producing some sound. Those sounds are reaching my head and my ear. So I am in a noisy environment. Now what the speaker is trying to do, control speaker is trying to produce some other sound which is trying to do a destructive interference with this noise source sound which is going to be coming, and reduce the noise which is there near the ear of the listener without the listener even wearing a headphone. This is the idea. And this is a control system type of a problem. It's a closed loop control type of a problem where I need to measure what is the level of noise reduction near my ear. So I have some microphone near my ear, but that is also not in a headphone. It is on the chair. Okay. So I will be able to do this entire thing and will be able to do a cancellation, and I use a control system for this. Okay. So these are some of the results which we are getting instant, what type of noise reduction which we can do. But to get a perspective, this would be a better picture. Better picture in the sense, these are sound levels in dBA. These yellows are, you can see, these are like 95 dBA and the blues are like 70 dBA. So this is the picture when I do not have a noise cancellation, or when I am not having any active headrest system active. So you can see the sound levels are at 95 dBA. But when I enable my noise cancelling system on the headrest, I am able to bring that to 70 dBA near the ear. Near the ear, you are creating a lower noise zone around the ear without you wearing a headphone. Okay, so this is an experimental result which we have done in 2023, where we did this performance evaluation and we showed in real time that this actually works and we will be able to do a noise cancellation. Okay, so this is the overall thing about this. These are some our work which we have done recently, 2024 2023, based on all of this type of things in the sense of beamforming and localization and DOA estimation. Okay, and these are some of the textbooks which are there, which are covering microphone arrays, because microphone array is becoming a very sought after area because of multiple reasons, because of this AI assisted devices, because of beamforming, all of those things. It is becoming very popular right now. Okay, fine. I think I can maybe stop here. Yeah, thank you. Yeah, if there are any doubts, yeah. I have skipped some of that math part, but I think if something is needed, we can go there. Thank you.
Thank you, Professor Nitin, for an excellent lecture.
Sir, thank you, sir.
Now, we'll invite actually some questions from the participants.
Sir, Tripathi here. I just want to know why the headphones are so expensive. I mean, varies from 35,000, 40,000 to 1.5 lakhs, or you may be knowing that it may be still higher. So what makes the features so expensive?
So see the microphones, depending on the quality of the microphone, can be very expensive because the diaphragm which is going to be used, the microphones which I have used in my experiment over here, these have gold diaphragms. So depending on the sensitivity and frequency response of my microphone, because I can have a cheap microphone which will not react to many of the frequencies. So I want to have higher quality microphones. That means creating microphone itself is costly. Second is these speakers over here. These are not generic speakers. These are called studio monitors. These have a flat frequency spectrum range over a wide range of frequencies. That itself makes it difficult. Third is the algorithm, because the biggest difference between your one particular ANC headphone and another particular ANC headphone is mostly in terms of the algorithm which is going to go inside and the processor which is going to be there, because these headphones have a power supply, have a battery, have a entire computer, I would say, on these headphones compared to a normal headphone which is only a speaker and some amplification. So all of these devices are making it costly, but it has become significantly cheaper now compared to the previous era. Yeah.
Professor Nitin, one minor clarification.
Yes, sir.
Are these noise sources are all uncorrelated with the signal or correlated? Some of them are correlated. What is the assumption?
So this can be correlated also, because in spatial filtering, because we have what you can say, because we have already identified the direction. Okay. Even if they are correlated, there is no problem.
No problem. Thank you. Yeah. Because the moment correlation, then detection becomes difficult. Yes.
Correct. Because even if it's correlated, not a problem. What I am saying is, otherwise array was not necessary. Otherwise, I could have solved that problem without going for an array.
Yes.
But now that we have got an array, then we are able to do the spatial filtering. That okay, only from that direction. Even if you have a noise which is correlated, it's okay.
Thank you.
Because it is not fully an adaptive filtering problem. That's what I wanted to say.
Exactly.
Yeah. It is mostly an estimation problem. Yes, sir. Yeah.
Sir, the question is whether we can put a helmet instead of a hearing aid. See, in an acoustic controlled auditorium, you have got a wall which reflects all the sounds and absorbs or makes it noise free for the all. So that is for a hall, but for a human being, can we devise a helmet which, if you are wearing, automatically all input sounds are getting filtered and then you are getting a pure sound?
So that helmet you are talking about is the hearable we are talking about, because we only need to control the opening of the ear. No, we don't need to worry about other parts. So these hearables or these small active devices, when incorporated with noise cancellation and noise reduction, understood, and all of these technologies will have to go inside that, then you will be able to get what you are talking about. You will be able to remove the noise, remove the distraction, listen only to one particular person, even when several people are talking. All of those will be possible.
Any other question?
Hi, Nitin sir. Hi, Nitin sir. I have one doubt.
Yeah.
So, as you said that the mics are mounted for this setup. Mics are mounted to the chair or maybe some other place. So when you move your head, let's say you move your head, okay. So the sense of directionality will be lost. Is it the case? Like, because the mic is on the different position and you move your head and the directionality will be lost, or you change, like you stand up from the chair and again the directionality, the sense of directionality will be lost, right? In this case.
Sense of directionality of the desired speaker is what you're asking about?
Yes. Yeah. Let's say the sound is coming from somewhere. So
Correct.
because the mics will be stationary only to the
That's correct.
chair, not to the like ears or headphones. So the
Correct.
directionality, sense of directionality for this setup will be lost.
Correct.
Is it the case?
Correct. Yeah. So there is a, what you're saying is correct only. There is a head movement is going to be a big problem in this setup. Okay. So we have actually done a head movement immune system where even if you are doing a head movement, you should be able to do a good noise cancellation. But here the advantage is I am only cancelling the noise. My speaker, my desired speaker is mostly in my friend or somewhere. I am not even cancelling there. Correct?
Yeah. So yes, sir, I got your answer. Maybe if we can install some IMU inside the speaker, like over the headphone, we can like correct the directionality.
Because what we want to do is that keep the user free. Means we are fed up with headphones. No, we don't want to wear any more headphones. We want to keep the user free and make the rooms intelligent or make your furniture intelligent rather than you want to wear any device. But I think we should be able to do, means we have done something on head movement immune, this active headrest. Okay, yeah. Thank you.
Any other question? So Professor Nitin, I have got actually one or two very simple doubts.
Sir.
Please tell me that why with age hearing loss takes place first?
Yeah. So I think I should have put the ear diagram. So there are multiple reasons. There can be this the hair cells inside your ear. There are these hair cells which are there inside the ear, which has been reacting to sounds for so long, for 70 years, 80 years. So it is like, it is something like you can say, what you can say, how will I explain? So the reaction to the sound, it has been doing for a long time. So now it will not be able to react to the particular type of a sound which is going to come. That is the crudest way of telling this problem. So by aging, anyway, hearing loss will be there. But one thing which we have to make sure is, if somebody is telling anyone that you have a hearing problem and you are prescribing a hearing aid, the biggest advice which is given right now is that if somebody is prescribed a hearing aid, always wear in both the ears, even if you do not have a hearing loss in the other ear. Because if you are not wearing the other ear will by default get hearing loss. So both ears there should be hearing aid. This is the latest prescription which is given to people, that do not try to reduce costs and say that I will put one hearing aid so that I am able to listen, because anyway you are going to buy the second hearing aid in the next few years to come.
Of course, now what we find, particularly with the younger people, or let us say in a day, 10 to 12 hours, actually they are using some sort of hearing aid.
Yes.
Is it really good, or it is really going to create further problem?
It is going to create definite problem. That is where this alert is coming. That is where WHO is saying that this is a serious problem, and serious problem because of prolonged digital audio exposure. That is the term which they are saying. And this problem is going to be very big for young population. And young population is going to suffer because of this situation. but the awareness is very poor, because when we are talking about health hazard, we are only saying, okay, cigarette smoking is hazard to health. Listening to music is hazardous to health. So,
Okay, answer. Now, I've got another
yes.
small query. There are many people, in spite of all these sophisticated hearing aids which have come up, still actually they are not able to hear. But definitely, if something could be there, we may be knowing what sort of device could be there, which can really directly convert speech to text, and at least text they can read.
Yeah.
Is there any device of that type?
Yes, sir. So now,
And wearable?
so speech to text has become a much more simpler problem right now with this AI based interpreter, means translators. So you can even have your applications on phone itself. Now phone will already, what you can say, translate it to you and give speech to text. So that the biggest communication problem is solved that way. But problem is people with hearing loss don't want others to know that they have a hearing loss.
That's
So we have to solve the problem in a much more milder way, what you can say, and sensitive way, rather than making people so much. Because I have a problem with my eye. I am wearing a glass. That is not a social stigma. All of us are happily wearing a glass. But I have a hearing loss. I am wearing a hearing aid. Is not that much, what you can say, understood or accepted. So that awareness and understanding and acceptance also will have to come. So that stigma is one problem which is there. So one solution which has come is that you could use like an Apple AirPod type of a device. AirPod is now a off the counter hearing device. So that you don't feel like you are wearing a hearing device, but you are able to get some solution out of it. But those are not the best solutions for you, but those are some of the directions in which the work is going on.
Okay. Thank you so much.
Okay. Yeah.
Now, actually, before I request Madam Renu Sharma to propose a vote of thanks, one thing that I would like to take your permission, since your lecture is being recorded.
Yes, sir.
Do you have any objection actually if it is circulated to
No, sir.
others? We can go ahead.
Go ahead. Yeah.
Okay, thank you.
Yeah,
The other part is actually in due course, actually, we'll be sending a small memento.
Okay. Yeah.
Nothing we can compensate your lecture, but at least a small memento we could send it by post.
Yes. Sir. Yeah.
Okay.
Okay.
I think now I will request Madam Renu Sharma to propose a vote of thanks.
Thank you, sir. Namaste. Very good evening to one and all present over here. Honorable Professor Damodar Acharya, Chairman, INAE Bhubaneswar Chapter. Honorable Vice Chancellor, Shikshanasandhan deemed to be University. Director, CSIR, MMT Bhubaneswar. Director, IIT Bhubaneswar. Director, NISER Bhubaneswar. And esteemed members of INAE and the participants, I first like to thank Professor Nitin George sir for giving a phenomenal lecture on microphone array signal processing and beamforming for therapies. Sir, you have taken up a problem which is very, very important, and the awareness about this particular topic is very less with the people. Hope this lecture, which once it will be circulated in YouTube, many will get aware of it. Sir, your lecture has addressed very serious problem with the technical problems which is available in the hearing aids and what are the solutions with that we have come up in this particular presentation. On the eve of this lecture, I would like to thank you for giving a lucid presentation, sir. And I request you to stay connected for further questions from the people, those who are not able to ask questions because of some reasons. Thank you, sir. Thank you once again. Namaste.
Thank you.
Thank you so much. Now there is an announcement. The next lecture is going to be on 25th of this month, and it will be given by a very renowned computer science professor from SOA University, Professor Lipika De. Okay. Now, with this, actually, we come to the closure session. So now I think we can log off.
Thank you, sir. Thank you.
So Professor Nitin, are you from College of Engineering, Trivandrum? Graduation. Oh.
He has left.